Hi, everyone. We are going to start in a couple of minutes. We'll give some 2 minutes time for everyone to join. Okay, we'll start in 1 minute. Okay, let's start. So, good morning, good evening. I figure there are people from different time zones. My name is Shimi Bandiel. I'm the CTO of Trainologic. And this webinar is about the Java memory model. I think it's one of the most important parts of the Java specification and the JVM specification to understand. And it affects almost every developer, whether you're working with Java or Scala or Groovy or Clojure. When you're developing applications on top of the JVM, it's very important to understand the topics that I'm going to discuss and show you with some examples and real-world scenarios. I'll just share my screen, and then we can start. Here it is. So, what is the Java memory model? Defining the Java language specification, the Java memory model describes how Java programs, how programs running on top of the JVM deal with shared memory regarding multi-threaded applications. Now, almost every application, is multi-threaded, whether you are creating threads by yourselves or there are threads running by the JVM itself, for example, garbage collection or etc. And the Java memory model is about actually 3 topics. It's about atomicity, visibility, and ordering. Let's start from the first one, atomicity. So this is a very simple topic because atomicity just says that what is an atomic operation inside the JVM? An operation that cannot be splitted. It's always, a single operation, and the JVM specification states that an atomic operation is an assignment to a variable up to 32 bits. For example, ints, shorts, byte, characters, etc. However, there are variables, larger than 32 bits. There are 64 bits variables like long and double. So what's the problem with that? The problem is that a JVM implementation may assign to a long or a double to 64-bit variables not in a single assignment operation, but in two assignment operations. Now, it depends on the JVM implementers, and the specification, encourages the JVM implementers to use atomic operation also for 64-bit variables assignment. However, it is not mandatory. How can it affect us? So let's discuss a very, popular class. If I would ask you what's the, the most known, immutable class in Java, many of you will say, okay, that's a string. String is immutable. String is used everywhere. It's thread safe. Let's take a look at string. Here is the string class. Now, when we talk about immutable classes, we expect an immutable class to have final members, immutable members. Let's take a look at the implementation of string. So we have the underlying character array. An array is not immutable, but it is not exposed to the outside in this implementation, so it is actually very safe. However, take a look at the second member, a private int hash. So here the hash is mutable. Okay, it's not final, it's default to 0, and so it must be changed, otherwise it has no meaning. So let's take a look at hash code. Here it is. Well, the hash member is used to cache the hash code of a string, because a string is usually, in many times it's the key in some hash map or is a value inside an hash set, and it's quite expensive to compute the hash of a string again and again and again, and because strings are immutable, we can cache the hash value. So let's take a look at this implementation, and we check if it's 0, we will compute the hash and assign it at the end. And if it's not 0, then let's use it as a, already calculated hash code. However, what will happen if we have several threads invoking hash code at the same time? Now, by first looking at the code, we may assume that hash code will be invoked only once. Okay? For a string, hash code will be calculated only once. However, if two threads will enter the method for the first time simultaneously, then hash code may be computed twice or even more time, depending on the number of threads and cores that we have. So is there a problem with that? Well, actually, no, because the hash code will be always the same, so we can, we can lose a bit of performance when calculating the hash code for the first time, and after that, it will be used again and again for all the threads. However, what will happen regarding atomicity? If hash code was long or double, this would not work, because here, on the line of the assignment, if this was not an atomic operation, then another thread may see a value that is not 0 and not the correct hash code. Fortunately, and I hope that it was by design, it is okay because hash is an int and is guaranteed to have an atomic assignment. Okay, so actually this implementation is very good. We don't require synchronized or volatile, and we're going to talk about synchronized and volatile on the next step. Okay, and that's actually it's okay. However, let's say that 1 year from now, they will change the JVM specification or the implementation of string, or the implementation of hash code, that hash code will return a long. Now, I'm assuming that if hash code will return a long and not an int, the maintainer of the string class may introduce a bug, because it's very hard, if you're not familiar with atomic operations, It's very hard to see the problem here. And then what will happen is just change it to long, and then we get a problem. We get a race condition. A race condition because the outcome of the application or the behavior of the application will depend on some random scheduling of the hardware and the operation system. So what I would do here is mark the member itself to note that this only works because we are using 32-bit assignment operation, and if it would be changed someday to 64-bit, then we need to take care of that. And actually, how do we take care of that? If we want to change the hash into long, okay, how do we say that, okay, now we need to deal with atomic operations? Then we will introduce volatile. And we are going to talk about volatile in depth. However, regarding atomic operations, a volatile variable, even if it is a 64-bit variable, will have atomic assignments on that variable. Okay, so if we would change the int into a long, then we should introduce a volatile keyword on top of that. And actually, I would recommend that if you are developing your own application and you are depending on, atomic operations for int or something like that, I would recommend put the volatile in ahead, so that if you need to change that, then you will not introduce a very serious bug into your application. So that was regarding atomic operations. Now let's talk about the second topic, visibility. Now, in the Java language specification, regarding visibility, it says that a thread can be seen as working with its internal caches. So if you update something in one thread, maybe it would not be seen from another thread. And this is actually not because of some, compiler optimization or operation system scheduling. It's because of the hardware, because of caches. We have multiple cores today for every machine and even for cellular devices. And when you have multiple cores, usually they have their own caches. So if I, in my thread, update a variable, let's say that I have a person with its name and age shared between two threads. The age is currently 20, and one thread will update the age to 21 at 8 o'clock in the morning. Now, let's say that thread number 2 tries to access the age 5 minutes later. Will it see the update for 21, or will it see the previous value? And actually, we cannot know, because maybe the update that thread 1 performed was or has happened on a cache, on level 1 cache for its specific core it was running on. And maybe the second thread will not see this value. So how can you actually program like that? Because if I update something from one thread, how do I have the guarantee to see it from another thread? Well, actually, the Java language specification states that it depends on some scheduling of the operation system and the hardware. However, you have something called memory barriers. A memory barrier will guarantee the synchronization of visibility. We will make things visible. And we have two built-in mechanisms into the language itself. We have the synchronized keyword and the volatile keyword. So synchronized, and I'm not talking here about, whether a thread can enter a critical section or block and wait for another thread to finish. I'm talking only about visibility. When a thread enters a synchronized block, it will see everything that was made visible by other threads. When a thread exits a synchronized block, every change that thread made will be visible to other threads. And it is actually quite expensive. And this is actually the main reason why we should not use classes like vector, which is actually a synchronized array list, or hash table, which is a synchronized hash map, because I will pay the price even for single-threaded applications. Because even in a single-threaded application, when you use synchronized data structures or the synchronized keyword, then we pay the price of making things visible, introducing, assembly operations that will, just flash things across the cache lines. The other keyword that we have is volatile. And a volatile member is always visible. It's like having the variable itself in the main memory. It's like we are not using caches. And actually, if you take a look at Wikipedia and see what's a volatile in Java, Wikipedia will say, okay, you have the value in the main memory. However, this is not correct, and I'm going to show you an example. Here it is. So, let's see. We have here some example. We are running 2 threads. Now I have a multi-core machine. Okay, so the threads are actually running simultaneously. Okay, and each thread will increment its own counter. I'm not sharing the counters. Each thread will increment its own counter and a large number of times. Okay, we have here 2 to the power of 27. And I will measure how much time it takes for each thread to update, to increment its counter. And let's run it, and I have 2 counters, C1 and C2, one for each thread. Let's run it, and it's very fast. Okay, each thread is like, how much is it? 17 milliseconds, something like that. Okay. However, I haven't used either volatile or synchronized, so the counters are not visible. Let's say that we have another thread number 3, and it wants to, see the values of these counters. It will see incorrect values, probably, because the counters reside in registers and in, memory cache lines. So let's make them visible. So I'm not going to use synchronized because it is extremely expensive. Let's use volatile. Here. Just making 2 members volatile. And that's it. It's the cheapest solution on top of the JVM. And now you can see that it takes much longer. Here, it took 6.5 seconds for each thread to finish. And if you will try to profile this application and check where is the bottleneck, you will not see anything. You will see that the threads are, spending the time in the loop. There is no blocking because of synchronization or something like that. It is, we are assuming it's threads going to the main memory and back, and it's, it takes longer than to update something inside their own caches. However, there is a very nice trick here to improve the performance dramatically, and it is called padding. Let's see it. I'm adding 8 long members, and I'm not going to use them. Here it is, just adding them. Remember, it was 6.5 seconds. Now I run it again, and we have 1 second. Wow, that's amazing. And I haven't used these variables. Now, first thing, don't go now into your code and introduce, 8 longs everywhere. Most probably it will not improve anything. It will just, a bit of reduce your performance and, incur a lot of, memory overhead. So what happened here? Now, the reason that the padding improved our performance is because how volatiles work. So a volatile is not actually going to the main memory and back. That would take so much time. And actually, volatile variables, they sit in the caches for each core. So if you update a volatile value, a volatile member, so it may be updated only inside your own cache, on your core that you're running on. So again, it doesn't explain anything. So, but the volatile, what it really means that if the same volatile resides in another core, in the cache of another core and I update the volatile in one core, it will automatically update the volatiles on the other cores as well. It will actually, now it depends on the hardware, but it can, stop the CPU for a second, or a lot less than a second, but it will stop the CPU for a second and then update its volatile. So a core will, just update, it's called cache coherence. It will update the entire cache lines for all the other cores. But still it doesn't explain. It's not like, we have two threads working on the same counter. That would make a lot of sense, stopping one to update it. But we have two threads working on two different counters. However, it is just like, working with the hard disk. Let's say that we want to update a single byte or read a single byte from the hard disk. So what? Do we take the single byte from the hard disk and bring it into memory and then perform some manipulation on top of that? No. When we access the hard drive, we get a sector, we get a block, because that's the way it is implemented. And the same goes for caches for the cores. When you want to have a variable from the main memory put on top of your cache, on your level 1 cache, then the actual hardware will take a cache line, will take a block from the main memory and put it on the cache. And the block depends on the hardware, but it's usually something like 64 byte. So when we had this scenario, when we had two members, one after the other, most probably, a thread wanting to read and update C1 will get a block containing also C2. And the same goes for the other thread. When thread number 2 wants to read and update the member C2, it will get the block containing also C1. And then the thread is updating C1, the same variable, the same volatile resides on another cache. So it will have to stop that CPU and update its cache value. And the same goes for the other thread. The thread number 2 will try to update C2, and it will stop cache number 1, the core number 1. Okay? So one is interfering with the other by putting a padding, by putting, 8 longs, which actually is the size of my cache line. I'm separating, I'm guaranteeing to separate C1 and C2 into different cache lines. Now each thread will work on its own cache line and will not interfere with the other core. And we get a tremendous boost in performance. Now you can see that this is still not the 17 milliseconds that we had when we were working without volatile, and that is because when you have a volatile, it will go to the cache. It will always update the cache, and if you're not working with volatile, everything will happen inside the registers, and then that will be, of course, much faster. But you can see how important it is to understand the concepts of cache lines and the padding. Now, this is a very simple example, and it's not a real-world example. However, let's consider the following. Let's say that we have, and it happens in a lot of applications, we have a thread pool and some job queue. Okay, and my threads are, polling on the queue, getting the jobs and running them. And we have, let's say, 10 threads, and we have the same available number of cores. So the threads actually can run simultaneously. And my application is super fast. Each thread can process 100,000 requests per second. Okay, so totally I'm able to process 1 million requests per second. And everything works fantastically. Now, let's say that we want to introduce some management console. And in the console, we want to see how many requests have we processed. Okay, just a counter, and we want to see it every half a minute or something like that, or every 5 seconds. Okay, so how do we introduce some counter like that? Well, we can say, okay, let's provide a shared long variable, and then everyone will update that long variable. Okay, but remember visibility. We will not have visibility, so we will not get an accurate counter. Okay, so let's make it volatile. It's the cheapest solution, as I've said. Well, making a counter volatile is not good enough because volatile can guarantee only assignment to be atomic, but we want to increment. We want to do a plus-plus operation. So for that, what we can do is use an atomic variable. That's what most people would use, an atomic variable, atomic long in our example, but there are also atomic integer and atomic boolean. And atomic variables are actually volatiles. You can see in the implementation, we have the value is a volatile, but it's a volatile, volatile plus plus, I say. It's a volatile, but not only regarding assignment and read, get and set, but also, something like increment or decrement. You get an additional operation that is also atomic. It is not actually something, built into Java specification. It is implemented in JNI code, in native code, by using, specific assembly operations. And you can see that I have a method like, increment and get. You see, I'm going to unsafe to something which is native, get and add long. Give me the increment and then give me back the value. So we can use an atomic long, and for our purposes, it's actually has the same semantics as volatile. Now consider the problem. I have the same volatile value, the same atomic long, shared by 10 threads, each trying to write to it 100,000 times a second. And it happens on, 10 cores simultaneously. Now the first thread will want to update the volatile, but the same volatile resides on all the cache, in all the caches for the other cores. So we need to stop all the cores and update their caches. And actually that will mean that just by introducing that single volatile value, I'm making my performance to become extremely poor. It will not be 1 million requests per second. It will be, I guess, something like 100,000 requests per second. Sorry. Okay, so this is, and that's just for, getting the value once every half a minute or something like that. So what can we do? What can we do with that? So for want of a volatile, the kingdom was lost. So in Java 8, Java util concurrent gained a very interesting addition called a long adder. Now, a long adder can be seen just like an atomic long, but the implementation is very different. The implementation of long adder is something like, let's say each thread will have its own volatile. It will increment its own volatile. And then we will have a method called sum to get the sum of all the volatiles. And of course, every volatile will reside in its own memory, in own cache line. There will not be shared caches by using the same trick that we did with the padding. Now, each thread will increment its own volatile, and then one thread can just ask, what's the sum? And they need to be volatile in order to get an accurate sum. Now, the sum operation is a bit costly, but on the other hand, it happens only, every half a minute. And actually, that will introduce a counter without, hurting the performance of the application. And it's a very important class, especially used for, this kind of situation, like, metrics and counters. And you have also long adder, and you have double adder. So that is regarding visibility, and it is extremely important. Now, we've talked a lot about performance and some tricks with padding and, Java util concurrent long adder. However, I think it's more important to understand the problems that may arise if you are not using volatiles, or if you are, not doing the visibility correctly. Because the problem is when you have a shared mutable object. When you have a shared mutable object, every access to that object must be guarded. it's either volatile or synchronized or some atomic, or we'll talk later about locks and read-write locks and stamped locks and things like that. It's very important to guard all the accesses to a variable, because even if you use synchronize in 3 points of your application to access some shared mutable variable, it takes only one place that you access without synchronize to get race condition, to not get the visibility that you require. Okay, so now we'll see it in practice when we'll talk about the third topic. We'll talk about reordering. Now, reordering states that you write your code in a specific order, but then the compiler or the just-in-time compiler or the hardware itself can reorder your operations for efficiency. And there are a lot of rules what can be reordered and what cannot be reordered. And I'm not going to go into those rules because they are not that important. But a simple example will show you what I mean. Let's assume we have these 4 lines. We have A equals 1, B equals 2, C equals A, D equals B. Now, reordering means that the hardware or any agent like the compiler can reorder the operations, but it should result, or it must result in exactly the same results in a single thread. And that's the important part, but we'll get to that. So how can we reorder these lines and still get the same result? So actually, we can move line number 3 instead and swap it with line number 2. We'll get the same result. And actually, if we consider this very simple example, the only things we need to take care while reordering is that C equals A must happen after A equals 1, and D equals B must happen after B equals 2. And that's it. You can reorder in any way you deem, but you must, guarantee that these 2 restrictions will still be there. Okay? But that's a very simple example. Let's talk something very familiar to some of you. The singleton. And I'm going to, not talk about how to correctly implement a singleton, but to talk about a singleton as many people use. We have the instance, and we want it to be lazy loaded. Not that it is not lazy loaded without that. We have a private constructor, and many people will do it like this. And public static, singleton, and we have, this is the get instance method, and we say if instance is null, then let's create the instance, okay, and return it. And that's perfect. Very nice, very simple, but it's not a singleton. Why not? Because of a race condition. If 2 threads will simultaneously enter the get instance for the first time, then instance is null, and maybe both of them will invoke the new and will get 2 instances. So we can protect that by using the synchronized keyword. However, now let's say in my application I invoke get instance 1,000,000 times. Now the threads will not invoke it simultaneously, they will wait one for the other. Moreover, we will pay the price for visibility. For every invocation of a synchronized method or a synchronized block, we pay the flush the barriers, it's called. We'll pay the flush the barriers price. Okay, so there is a pattern called double check locking. Let's see it. We put synchronize inside the if, and then here it is. Now we do a double check. Here, this is a double check locking. Okay, and a very simple simulation will say, okay, thread number 1 enters, instance is null, we are gaining a hold of the lock, then the thread will be here, and then let's say we have another thread entering, but every other thread will just block on the synchronize until the first thread finishes, and then when the threads will enter the synchronize, instance will not be null anymore, and everything is okay. And after some time, every thread will just enter the get instance, we'll see instance is not null, and then we get back without paying the price for synchronize or volatile or anything. And it looks great, and actually if you will, do a lot of simulations, with pen and paper, it looks fine. Doesn't look like it has a bug. However, there's a problem here. It doesn't work. Why is that? Because of reordering. Or the reordering will be a problem here, but the problem is in the code itself. We'll get to that. So the problem is in the line instance equals new singleton. So what happens here, we have memory allocation, right? We have constructor, invocation, and we have the assignment. Here it is, the assignment to instance. Now, let's say, and it happens in a lot of applications, that in the singleton constructor, we need to load some property files and update members. Okay? Now, in order to load the property file inside the constructor, it's an I/O operation. Now, the CPU will see, okay, we have an I/O operation. Can I do something during that I/O operation? And the CPU takes a look ahead in the, in the pipeline, in the command pipeline, and see the assignment. And this assignment depends only on the allocation, because it's the actual memory reference, okay? And we already performed the memory allocation. So the CPU may reorder the assignment to happen during the I/O operation. And what may happen then is that the thread will update the instance, and then another thread will enter the method and may see instance is not null anymore. And then it tries to access the member, and it will get a default value instead of the value from the property file. Now, it will happen in extreme rare cases, but these are the problematic cases. This is a race condition. It will happen 1 out of 1 billion in production. And this is extremely scary. How can we deal with that? Now, what's the problem? Because, this is singleton, and we'll see the solution, and everything is okay, but it may happen in other places in my application. Where is the problem here? And again, the problem is always shared mutable variable. Who is shared and mutable here? It's instance. Instance is shared between a lot of threads, and it's mutable. We change it. So let's see if every access is guarded. So this write to the shared mutable variable is protected with the synchronized. This read is protected. However, this read is not protected. And usually this is a bug. Now we only need to find a simulation that will show that bug. But this is the bug. And actually, in order to solve it, what we can do is introduce a volatile. And in the Java language specification, a write into a volatile variable is guaranteed to happen after all the writes before that in the code. So actually here, the assignment will not be reordered with the constructor, okay? And again, we have, we have singleton implementations that are much more readable than this implementation, but I wanted to show you how important is the Java memory model here, okay? Now, almost in almost every case, if you have a shared mutable variable, you need to protect every access to that. There are exceptions, like with the string class we have seen, the cached hash code is not protected at all, but it takes very careful simulation, and going over all the possible cases to show that it is okay. And we prefer not to do that and just guard it, you know, with volatile, synchronized, or other mechanisms. Okay? Great. So now let's talk about locks and the price of locks. Okay, so I have a very nice example here. Just a second, and I will make of course, the code available. We have a Pacman. We have a Pacman, and a Pacman has two operations. We have move, and we have sum of position. Okay, and actually these two operations are actually read and write. Move is writing to the Pacman, and sum of position is reading the sum of x and y. And assume that Pacman has members for x and y, two ints, and we can move it and get the sum of position. Now let's say that we have a single instance for Pacman, and we have 7 threads working on that. We have one thread doing a write, a move, in an endless loop, just doing move, 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 move. And we have 6 more threads doing in a while true loop, in an endless loop, performing sum of position. Okay? And of course, we have a shared mutable object here. Now we need to guard against race conditions, and we have a lot of options. Let's discuss them. So the first one will be use plain old synchronized. Okay, here it is. We have a Pacman, call it Pacman sync. We have x and y, and we guard with synchronize both methods, both move and sum of position. Okay, we have another option. We can use, instead of synchronized, we can use Java util concurrent lock. And Java util concurrent lock, I will not go into all of its API, but on the basic level, it has a synchronized-like operations. We have lock and unlock. And no two threads can, you know, have the same lock in the same time. So one will wait for the other. And we also have a lot of other options like try lock, you know, do a non-blocking lock, or try lock with a timeout, or get some interruptibility feature. But I'm not going to discuss that. I'm going to discuss, you know, it's like synchronized, but whether it's faster or not, that's what we are going to check. So I'm doing a lock, and of course in a finally block we'll do the unlock, and again lock and unlock. And I'm going to show you another implementation using reader-writer lock. And a reader-writer lock, a lot of threads can hold simultaneously the read lock. A lot of threads can do sum of position at the same time, but not at the same time as one doing a move. Okay? So this is a reader-writer lock. So far we've seen 3 implementations. We have synchronized, we have lock, and we have read-write lock. Now let's test the performance. And I'm going to test that by using all of the implementations one after the other for 10 seconds, running 7 threads, and then measuring how much operations did we do in 10 seconds. So you see the synchronized approach and the number of operations. Again, the numbers are meaningless, but we want to compare them between one implementation and the other. So far we can see that lock performs better, way better, than synchronized. Okay, it's okay. So you see that the number of reads is something like 40% better than synchronized, and number of writes is 100% better than synchronized. So actually, you should use, you know, lock and the reentrant lock implementation over synchronized for performance reasons. You know, it's a bit more code to write, but for performance reasons, it's better. Now, we would expect that read-write lock will perform even better because we have 6 threads performing reads at the same time with only one thread doing the writes. However, let's take a look at that. We see the reads are way worse than even synchronized. You see, there's a missing digit here. It's 56 million compared to 107 million or 146 million. Why is that? Should be better. Should be way better. However, we know read-write-lock as a management overhead. You know, it manages a lot of counters and uses several volatiles and not synchronized, but several volatiles at least to manage its state. And it's very good class if you want to guard against, or you want to do a read-write-lock against I/O operations. But here we are only guarding a single, or actually not single, but two memory accesses, accessing X and Y. So it has a lot of management overhead. And you see that the writes are a bit better than the synchronized, but still much worse than, you know, reentrant lock. So it's not the good tool, or it's actually the worst tool to use for this specific example. Now, in Java 8, we have a new type of lock called stamped lock. Let's see it. And by the way, take a look at the performance. The number of reads is almost, you know, 2.5 times than the reentrant lock. And the number of writes is actually much the same. So it's a better implementation. And let's take a look at stamped lock. A stamped lock is like a read-write lock. Okay, I can use it as a write lock or as a read lock, but it also allows me to perform something called an optimistic read. An optimistic read is actually, I'm not locking anything. I'm just getting a stamp, a long value. And I can do my read, here I'm reading X and Y, but before I use the value that I read, I want to guarantee that no write has happened. So actually, no thread has gained the write lock before I finished reading. So I can validate my stamp and get a true if it's validated, or if I get a false, I will just try and do it again. And this is a very simple example. In real-world code, what you will do is try the optimistic read several times, maybe, you know, 20 times or 200 times. And after that, you will resort to, you know, having a full read lock, okay? And you see that the performance is way better than the other lock implementations. However, there is a huge price for locking. So let's take a look at the most interesting example called unlock. And before that, let's take a look at the performance characteristics. The reads are the, you know, the best ones so far, and the writes are way better than every other lock implementation. Let's take a look at that. So we have Pacman unlocked, and here it is. So before going into the implementation of Pacman, I'm introducing a new class called position. Now, position is an immutable class. You see X and Y are final. You cannot change a position. You can only get a new position. And now Pacman, instead of having X and Y, will have a position in Pacman, and actually a volatile position, an atomic reference. Remember, atomics are just volatiles plus plus with some additional operations. So we'll have a volatile position, and we only need to change the reference. That's the shared mutable object. Now, instead of having two members, two int members, X and Y, that we need to guard both of them simultaneously, now we have to guard only a single reference, only the volatile itself. So take a look at move. So in order to do a move, I'm taking the current, that this is just volatile read, getting the current position. Now I'm calculating a new position. I'm creating a new object here. I'm paying some price for memory allocation. And then, this is the special operation on atomics, I say, if it is still the same position, switch it to the new position in an atomic manner. And I'm getting a true if I've succeeded, and false if not, someone changed the position during, my computation. Now, in my specific example, there's only a single thread performing the writes, and so this will always return a true. If we had several threads writing to the pacman, then we may get false here, and we'll have to do that again. We'll talk about that in a second. And the sum of position is just a regular read. Now, remember, the performance was here much better than any lock implementation. On the other hand, you may say, okay, but you're allocating a lot of objects. You'll get, one day, a lot of GCs, a lot of garbage collection. You'll have pauses, Everyone talks about, garbage collection being problematic in Java and, causing some performance problems. And actually, in this example, I've not, enabled the statistics for the GC, but I can guarantee that I've run it a lot of times. We had a lot of hundreds of GCs performing during this test. And even with all the overhead of the GCs, which is actually nothing. I will mention the GC why in a second, but we had a lot of GCs here, a lot, hundreds of GCs. And still the performance was way better than any lock mechanism, because locks are extremely expensive. They hurt scalability. If you can, get rid of some locks in your application, almost any other approach is way better, even paying some price for garbage collection. Now, regarding garbage collection, in the JVM, if you just allocate an object and it is discarded almost immediately, you pay no price for that regarding GC. And actually, this is what happening in our example with the position. The thread is doing a while true, allocating, millions of new positions, but, discarding the previous ones. And the GC happens a lot of times, but it is extremely fast. It just, doesn't even go over all of this garbage. It just, moves the pointer of the allocation to the beginning of the heap, and then that's it. All the garbage will just be overridden by, subsequent allocation. And that's, very interesting, because the approach for immutable objects, using immutability over locking, is usually better. Not always, but usually. And there is another implementation at the end. It's not that interesting, because it's very specific to this problem, but I'm just going to show it as well. Because our mutable state is two ints, x and y, we can combine them into a single long using bitwise operations. And then if you have a single long, we can use atomic long, and now it will work even without allocations at all. No GCs here, and this is the fastest approach, but it will not scale. Just add an additional Boolean, and that's it. You cannot do that. You don't have 65 bits variables in Java, okay? So I like very much the pacman unlocked approach, okay? And it shows that you can actually fight the shared mutable object in 3 different ways. The first way to deal with shared mutable objects is what I called a commando mode. In a commando mode, you just need to deal with every access. You need to use synchronized or volatiles or atomics, Java concurrent something, and it's very hard, it's very error prone, and it's very hard to get the performance right. This is the most important part. It's very hard to get the performance right. And you can get, very good or extremely good performance. On the other hand, you may introduce bugs. And this is the first approach. The other 2 approaches are solving, the problem at its root. It's not used, if you have shared mutable object, then let's either use unshared mutable objects or use shared immutable objects, okay? Now in Java, it is extremely hard to use shared immutable because we don't have, built-in data structures for that. It's somewhat easier in Scala and maybe, using some other third parties for Java. But a very common approach these days is to use unshared objects. How do? We use unshared mutable objects. Well, actually, we use some kind of a framework. And in the Java ecosystem, we have several frameworks for dealing with or providing us with, unshared mutable objects. One of them is very popular framework called Akka, the actor model. Another framework is Vertex. It's something like Node.js. If you take a look at the JavaScript ecosystem, we have actually no problem there, and we have a lot of scalability, and the performance is great. And this is mainly because we are not dealing with shared mutable objects. We are dealing with unshared mutable objects, but we need a framework for that, okay? And I actually prefer both approaches over the commando mode, over, dealing with it ourselves. Okay, so now you can post questions, and we will be able to answer them over the channel. So I will just, remove the screen sharing. Okay. And let's conclude. So, So we've covered the Java memory model, talking about atomic operations, visibility, and ordering. And I think it's extremely important for every developer working on the JVM to understand the problems that may arise with shared mutable objects. And I hope that now you understand how can we deal with them. Okay, and also we've seen the performance penalty for working with the incorrect implementation of locks and volatiles and all of the other, tools. And it's also very, very important to understand that it's not for every application. For example, I've talked about having a thread pool, accessing some queue, and performing a lot of operations, and I want to introduce a counter, so we should use long adder or some other tool. However, if your threads are just, writing into some, a relational database, then it doesn't matter. It doesn't matter at all, because writing to relational database is way slower than any other synchronization mechanism for any counter that you want to introduce. So it depends on the application. But now we've seen the right tool set. Okay, and you understand the principle, and you can actually write low latency or near real-time applications in Java. And it's not only for Java, it's the same for Scala and Groovy and Clojure, because everything here is JVM level. It's not Java specific. So in Java, you have the synchronized keyword and the volatile keyword, but in Scala, you have volatile annotation, but it's the same. It has the same meaning. Okay? So I hope you enjoyed that, and it was just a part from our low latency training and extreme Java training. And we will be happy to answer any questions you have over the chats, and you can send emails to Trainologic if you have any more questions. And I hope you enjoyed that. Thank you very much.